So here we have double tube or double tube counter flow heat exchanger. So the flow direction is counter. So hot fluid goes in one direction and the cold fluid goes in the other direction. So we have two tubes. So we know the inner diameter of the cold fluid and we know the outer diameter for the hot fluid. So the mass flow rates are given 0.5 kilogram per second and 0.8 kilogram per second. And let's say for the sake of simplicity, so we are told that the cold fluid is at 45 degrees Celsius average properties, and this is at 80 degrees Celsius. So we are asked to find overall heat transfer coefficient for this system. Okay? So let's take a look at this. So let's start to list our knowns. What do we know in this problem? We know TW, T out, so water phase we know, oil phase we know, T oil, diameter of inner wall, diameter of outer wall, and we know the mass flow rate for water, mass flow rate for oil. Our goal is to find overall heat transfer coefficient, U. So we'll assume, so the thermal resistance of the inner tube, thermal resistance of the inner tube is negligible. Since we don't know the thickness of the wall, so that already implies that we need to cancel, we need to omit it. So we'll assume the flow is fully developed. Flow is fully developed for oil and water. Again, in chapter 8, we learn how to test this. So you have the criteria to decide if the flow is fully developed hydrodynamically or thermally. So you need to always do this calculation. So in this example, so we are assuming this, that it's fully developed, but this is not always the case. So we'll also assume that the properties are constant. Okay. So let's list the properties here. So we need to put the properties. So we have oil phase and water phase. So for water at 45 degrees Celsius, so we have density, which is 990 kilogram per meter cube. So we have thermal conductivity, which is 0.637 watt meter per Kelvin. The Prandtl number is 3.91 and kinematic viscosity is 0.6 10 to the minus 6 meters square per second. So for oil at 80 degrees Celsius, so the density is 852 kilogram per meter cube. Thermal conductivity is 0.138 watt meter per Kelvin. The Prandtl number is 490 and kinematic viscosity is 37.5 10 to the minus 6. So what we need to do here, the approach is basically as follows. We find H inner, we find H outer, and then we'll find 1 over U, which is 1 over H inner plus 1 over H outer. So now let's focus on the inner tube inside, which is inner tube. So we know the diameter is 0.02. So I would like to calculate the mass velocity, which is mass flow rate divided by rho times AC. Mass flow rate divided by rho times pi d squared over 4, and this is for the inner side. So for the inside, we have here cold water. Let's call this one as water. So 0.5 kilogram per second divided by 990 kilogram per meter cube. Pi, diameter is 0.02 square meter square. So if you do the math, you'll get 1.6 meter per second. And after we have the velocity, we can calculate the Reynolds number. U water diameter divided by kinematic viscosity. 1.6 is the velocity. Diameter is 0.02. Kinematic viscosity is 0.6, 10 to the minus 6. Everything is in metric unit, they will cancel. So we have 53,490. So this is greater than 2300. So this means the flow is turbulent. So we have a turbulent flow. So now for the turbulent flow, so we'll be using this equation. So this is the equation that we talk about in chapter 8. So this is for the turbulent flows. So we have Reynolds number to the 4/5 power, Prandtl number to the n power. N is here is 0.4. N is here is 0.4. This is for heating. This is similar to the mini exam. Basically, Ts is greater than T mean. So since water is cold and outside is hot, water is being heated. So N is 0.4 instead of 0.3. So you calculate the Nusselt number. So you plug in everything. So we have Reynolds number here, 53,000. And the Prandtl number was given. This was 3.91. And you can carry out the math, and you will see that this is 240.6. And for the turbulent flow, we'll assume this is also equal to average. So that means I can calculate H simply by K over D Nusselt number. So K is for water 0.637, diameter is 0.02, and the Nusselt number is 240.6. So you have 7,663 watt meter square per Kelvin for H inner. Okay, so we calculated this one. So this is an internal flow, and it's a turbulent flow, and we assume it is fully developed, and this is the equation we use for this case. For the outer flow, for outer flow, this is annulus basically. So we are interested in basically inner section of the annulus. So if you just think about this, so we calculated H in here, H out, we are here, we want to, this is H out. So this H out is actually inner part of annulus. Okay, so this is what we must calculate. So to calculate this, so we need to calculate the Reynolds number. So the Reynolds number depends on the hydraulic diameter. For an annulus, the hydraulic diameter is the outer minus the inner, 0.03 minus 0.02. So this is going to give us 0.01. And the mass flow rate is mass flow rate of oil divided by rho AC. So this is mass flow rate of oil, rho, pi over 4, the outer square minus the inner square. So you'll have 2.39 meter per second. This is the velocity at outer region and the annular region. Reynolds number is velocity of water, so the velocity of oil, hydraulic diameter divided by rho. So if you plug in the numbers, velocity is 2.39 in metric unit. Diameter is the hydraulic diameter is 0.1 in metric unit. And the kinematic viscosity of oil is 37.5 10 to the minus 6 in metric unit. So you get 6.37. This is less than 2300. This is laminar flow. And we assume it is fully developed. So we need to go back. So you need to go back to this table. So this is the table in chapter 8. So we talk about this in your textbook. So in chapter 8, so in the previous slides. So our goal is to estimate Nusselt inner for the annulus, which is going to give us H out for the system. Okay? So this is H out. That's what we care about. So this is H in, this is H out. And there is another H that we don't care about. So this, right now we are carrying inner section of the annulus to calculate H bar out for the system. So to use this table, I need to calculate the I over the outer. So this is 0.02 for inner, 0.03 for the out. The ratio is 0.667. So now, we need to interpolate in between these two. So we are assuming one surface is insulated, the other is at constant temperature. This is the valid case here. So we interpolate in between these two. So we need to interpolate between these 2 points. So the Nusselt number, so you need to interpolate it, Nusselt number. So basically, Nusselt number inner is 5.45. Okay? So that means if I want to calculate H bar for the annulus, this is for the annular region, H inner annular is equal to K over dH times Nusselt number inner. Okay? And in this case, so let's say first H inner. So that means 0.138 in metric unit for the oil, thermal conductivity of oil. Hydraulic diameter is 0.01 and the Nusselt number is 5.45. So you get 75.2 watt per meter squared per Kelvin. So that means H inner. So since it is fully developed flow, so we'll assume this annular is equal to H inner annular. So that means the overall heat transfer coefficient, is equal to 1 over H inner plus 1 over H outer. So this is going to be 1 over 76.63 plus 1 over 75.2. So if you plug in everything, you get U is 74.5 watt meter square per Kelvin. So we assume here, okay, so to be able to use this graph, we assume one surface is insulated, the other surface is at constant temperature.